guys, so in this video we're going to do some more examples of real-world exponential growth and decay problems. So let's read this first one. It says, recall our bond fund where the rate increase was 6.2%. So this is actually talking about another problem that we had talked about in part 1 of this video, but we have the information that we need here. It's an increased rate, so that means that it is growth, and the rate is 6.2. Now remember that the factor is 1 plus or minus the rate as a decimal. Okay, now it will be plus if it is growth, if it's exponential growth, and it'll be minus if it's exponential decay. So first, let's go ahead and change 6.2% to a decimal. So that means we're going to have to move the decimal twice to the left, which means that we would put a 0 for a placeholder in front. So the rate is 0.062. And the initial amount, remember the initial amount is the y-intercept, which is the b value. It's the a value. In the format that we use for exponential functions, which is f of t equals a times b to the power of t. Of course, a is that y-intercept, like I just mentioned, and b, well, let's cover b first. B is the growth or decay factor, which again is found by, if you have the rate, if you're given the rate, then you add or subtract to 1. And then t is like how many times you are going to calculate that factor. And then the output is the amount that you have. How much is in there? How much money? How many bacteria? What is the population, the amount of population, whatever the problem is. Of course, this one we're talking about money. So in this case, we are talking about amount of money. So we're going to go ahead and write the equation that represents the exponential growth of the bond function. And again, we know that it is growth because it is increasing by the rate, okay? So let's go ahead and write our function f of t equals, again, the initial amount is a, so that's 1,500, and then times the factor, since this is growth, the factor b would be 1 plus, since it's growth, we're going to add 0.062 plus the rate. So b is 1.062. So this is 1,500 times, we can also use parentheses for multiplication, right? 1.062 to the power of t. So that is the function. How much money would be in the account at the end of 10 years? Okay, so they're saying how much money is in the account after 10 years. Now we have to figure out how this is being calculated, right? The rate of increase is being calculated per year. They don't actually specify that it's per year, but if they don't specify the rate of a, like how many times the rate is being calculated, then we assume it is per year. So in 10 years, this rate would have been calculated 10 times. So this means that t is 10. So let's find f of 10, which we would have to do first the exponent. Oops, I have one more 0 there. First, we would have to do the exponent, 0.62 to the power of 10. So I'll grab my calculator for that. Oops. So 1.062 to the power of 10. And then now we can multiply. Remember, in order of operations, we do exponents first, then multiplication. So we end up with 2737.388425. Now this is money, right? And this is the amount of money that we have after 10 years. So we would have to round the nearest 2 decimal places because money doesn't make sense for me to tell you, oh, give me 0.388425 cents, right? We say 39 cents. So we'll go ahead and we'll round it to 39. So we have $2,737 $39.38. Is that what we said? I already forgot the number. No, 39. Okay. In part C, they're pretty much asking us for the same thing, except instead of it being 10 years, we're going to change that to 20 years. So we're finding f of 20. So again, you're just plugging in 20 for the years. And again, you can use your calculator. Now you can, if you have a scientific calculator, usually I don't think that there are any scientific calculators that don't do operations properly. So if you put it in all together in your calculator, if you can, it will give you the correct amount. I sometimes, just to be better safe than sorry, will go ahead and will do the operations as I know they should be done, and I don't really rely on the calculator. But this one does it correctly, and I know that, so there you go. So $4,995.53. $4,995.53. Or was it 35? No, 53. Okay. Part D is asking us to go ahead and sketch this. Now, the x-axis and the y-axis are not labeled, so that's what I will do first. Again, remember the input is the amount of times that this is being calculated. Of course, the time is in years, so the x-axis will represent the amount of years that have passed, and the y-axis will represent the amount of money, how much money is in the account. Okay, now we already have some values here, right? We have when t is 10, we get 2737.39. We can use that for graphing. And when t is 20, we get 4995.53. Okay, so we can go ahead and graph those. So I'll actually go up by tens on the x-axis, and I won't label all of them just for, you know, the sake of time. And we have to go up to at least 5,000 on the y-axis. So let's go up by 500. So 500, 1,000, 1,500, 2,000, 2,500, 3,000, 3,500, 4,000, 4,500, 5,000. So I'll go ahead and plot the 10 and 27, so roughly around here, halfway between 2,500 and 3,000. And I will plot 20 and 5,000, so very close to 5,000. Okay. Now, on this graph, it's not that precise because I only have 2 points, right? And obviously this is an exponential function, so I need more than just 2 points. So I'm going to go ahead and plot some other points. I'm going to go ahead and plug in 0 for x and see what the y value is. And then I'm going to go ahead and plug in 25 just because I want to see what it's going to be here. So I want to figure out what is my y-intercept, which we already know is 1,500, and then I want to know what is the y value for 25. So obviously plugging in 0, anything to the power of 0 is 1, so 1 times 1,500, that's why the y-intercept is a, is 1,500, so that gets plotted there. And then for 25, I'll use the calculator, and I can actually, with this calculator, go back to this equation that I entered, hit enter, and then change this 0 to a 5, and then hit enter, and that gives me 425. So for 25, we have 67, 48, 45. Okay. For 0, we had 1,500. I'll just write that down. Okay. So at 25, we have 67. So it's actually going higher than this would be 6,000. So it's like up here somewhere. So it's getting, you could see that it's getting exponentially bigger, right? Remember, exponential growth, you start off kind of slow and then you quickly go up. So I will start from here. Obviously, we can't have negative time. We can't have negative amount of money, but we can if we leave this in the account. And I'm doing a terrible curve. Let's try that again. If we leave it in the account, in theory, we will get more and more money over time, and our money will exponentially grow. All right, so let's go ahead and try another problem. And I want you to pause the video now and try this one on your own. Okay, so this one is talking about fish population. Okay, now the rate here is a decrease. So this is actually decay. And the decay is by 5%, which is 0.05. So the rate of decay is 0.05. So the factor will actually be 1 minus 0.05. Since this is decay, we will subtract. 1 minus 0.05 is 0.95. So this is our B value. And we do have the initial population, which is 14,204, and that's our A value. So write the equation that represents the exponential decay of the fish population. Sure, f of t equals 14,204 times 0.95, our B value, to the power of t. Now, part B says, what will the fish population be after 10 years? Well, let's find what is f of 10. And again, you're just plugging in 10 in for t. So 0.95 to the power of 10. And I will plug it into the calculator all together just to save time. So 0.95 to the power of 10. And we get 8504.45, etc. Now, what is the output? This is the amount, right? Amount of what? Amount of fish, right? Our fish population. So we can't say that we have 0.45 of a fish, right? We only have whole fish. So we will say that that is 8,504 fish. Okay. And then part C is asking us, what about after 20 years? So we're just finding f of 20. And again, you're just plugging this into the function that you just said this was the function rule for any time t. Now we're using 20 for time t. So I'm just going to go ahead and replace the 10 with 20. And we get 5,000, and we'll round that last fish to the whole fish, so we'll say it's 5,092 fish. Technically, you know, we haven't lost that last fish yet, but we'll go ahead and round it to 5,092. Okay, so let's go ahead and sketch this graph now in part D. So in part D, we're sketching the graph, and again, our x value represents time, which is in years in this case. And the y value is the amount of fish, right? Is the fish population. Okay, so again, we do have some input and output already. We do have at 10, we have 8504. We have at 20 is 5092. And we also have the y-intercept, which is the initial, what we started with, the amount of fish, which is 14,204. I think with these three numbers, we would be good enough to graph, but let's just go ahead and graph it, see what it looks like, and then determine if we need more later. So I'm going to go up by 5, so 5, 10, 15, 20, 25, 30, 35, 40, etc. And on the y-axis, I do need to go all the way up to 14,204. That will be my highest y value. It's decay, so it's going down from there. So I do need to reach 14,000, which is actually quite a bit. So I think I'll go up by 1,000, 1,000, 2,000, 3,000, 4, 5, 6, 7, 8, 9, 10. Nope, not enough. So we need to go up by 1,500. So 1,500, 3,000, 4,500, 6,000, 7,500, 9,000, 1,000, 10,500, then this would be, so we're adding 3,000 every 2 units, which actually makes the math a lot easier in my head. So I'll just go ahead and do that. So this is 12,000, this would be 15,000, and this would be 18,000. Okay, so now we can go ahead and plot these numbers. So 0 and 14, 204. So this would be 13,500. So it's higher than that. So it's like roughly halfway through here. A little bit bigger than 13,500. Then at 10, we have 8,500-ish. So that'll be pretty close to 9,000. So roughly about there. And then at 20 years, we have 5,000 fish. In between here is 4,500. So 5,000 will be somewhere between these two, but a little bit closer to 4,500. Okay, and if I wanted to be a little bit more precise, we could go ahead and add one more point. Let's go ahead and find what the output is when the input is 40. So at 40 years, how many fish do we have? And that's 1825. So at 40 years, we have 1825. Remember, this was 1,500, so it's just a little over that. All right. So I'm going to go ahead and connect my dots now. And again, remember, we can't have a negative amount of years or a negative amount of fish in this scenario. So we will eventually have some x-intercept. And after that x-intercept, we won't, continue the graph. So this is a little deceiving, putting this arrow here, because you can't have a negative amount of that, but we'll just keep that in the back of our head. We definitely won't put an arrow on this side because that would be for a negative amount of years. All right, let's go ahead and try one problem. And again, I'll give you guys some time to pause and try number 2 on your own. Okay, so the rabbit population in Central Park was 150 in the year 2000. So this is what it started at in the year 2000. The population is increasing by 11% each year, so by a rate of 0.11. Define the variable for the function and state what the variable represents. Okay, so let's go ahead and say t is our input, f of t will be our output. So t, our input, is the amount of years that have passed since the year 2000. And f of t will be the amount of rabbits, the rabbit population that is there, determining, of course, on the amount of years that has been since 2000. So what's a reasonable domain for this situation? Remember, we're looking at the input. So what is a reasonable domain for the years? What are reasonable numbers for years since 2000? Well, definitely not negative numbers, right? So it would have to be either we're still in the year 2000, so no years have passed since 2000, and then essentially, right, in theory, it could go up to infinity. Now, we could argue that maybe eventually there will be a point in time where Earth will be no more, there will be no more rabbits, or Central Park will not exist, but obviously these are like special circumstances, but definitely years can't be negative, and in theory they, we could go on to infinity of time. They're asking us to write the function that represents the exponential growth of the rabbit population. So I already have the a value, the y-intercept, the initial amount is 150, and then the b value, since this is growth, the population is increasing, it will be 1 plus 0.11. So the b value is 1.11. So the function here, right, we said our output was f of t, so we'll go ahead and write this as f of t equals 150 times 1.11 RB value to the power of t. And then the last one says, what will the rabbit population be in 2025, assuming that the annual growth rate obviously stays the same. So if at 2025, it would have been 25 years since 2000. So t would be 25. So we're finding what f of 25 is. We're finding the output if the input is 25. And again, we could just use our calculator for this. 150 times 1.11 to the power of, oh, I think I put a few too many ones there. So let's try that again. 150 times 1.11 to the power of 25. And we get 2037.82. Now, again, we have to determine what's the output. The output is rabbit population, so it doesn't make sense to have a decimal here. We will have only whole numbers. So we'll round that to about 2038 rabbits. Okay, let's go ahead and look at number 2. And like I said, I will give you a moment. Go ahead and pause this video now and try it on your own. Okay, now this problem says a new Honda Civic costs $24,500, so that's what you paid for it. But they tell you that it loses 9% the moment you drive it off the lot. So really, the initial value of the car is not $24,500. That's just how much you paid for it. The initial value of the car will be whatever $24,500 is minus the 9%, which is 0.09 of that value. So let's find the A value by making that calculation. So we have 24,500 minus the 9% of that value. Okay, so what the car's initial value is once you buy it is actually $22,295. So you just bought it, no time has passed, but because you just bought it, the moment you drove it off the lot, it decreased in value, and that's the value that it is now. Even though you just bought it, you wouldn't be able to sell it again because then it wouldn't be considered new. It would still be considered used, even if you just bought it. So this is actually the initial value of the car. Now it says over the next 4 years, the Civic depreciated, so you're losing value by this rate each year. So you're losing by a rate R of 0.105. Okay, 0.105. So the factor B, since it is depreciating, this is decay, right? And so for decay, we're going to subtract from 1. So we're going to do 1 minus 0.105. And of course, you can always use your calculator if you struggle with doing simple decimal calculations, even though I really don't think that it is necessary. But you can see, you can subtract, you get 0.895. Okay. So now we have our initial value, we have our factor, and the last sentence tells us that after 4 years, the car is valued at 58% of its original cost. Okay, so this will work only for 4 years. Determine the variable for the function and state what the variable represents. Okay, so we'll do t and f of t for input and output variables again. T is the amount of years that have passed since it was purchased. And F of t then would be the output, which is the value of the car, the value in money, of course, of the car, which is specifically the Honda Civic. Okay, now what is the domain that best fits this situation? Okay, remember domain is what are the possible values for the input. Now again, you can have a negative number of years, so the smallest amount of years that you could have passed since you purchased this car is 0. Now, in theory, we could technically own the car for forever. But remember, this is the domain for the function in particular. And remember, in the situation, they told us that this depreciating value is only for the next 4 years. So after 4 years, we don't know exactly what the depreciation is going to be in rates, right? So this formula, this function will only be useful and valid to us for 4 years, up till 4 years, and that is it. Now they want us to go ahead and write the function, so f of t equals our initial value, 22,295, times the factor, which is 0.895, to the power of t. And the last question asks us to use the function to prove that after 4 years, the approximate value is 58% of the original cost. So let's go ahead and find what 58% of the original cost is. Now, 58% of the original cost was $24,500. And 58% of that, 0.58, of that original price is $14,210. So they're saying that it would be $14,210. Now, all they're asking us to do is to use our function to show that that is actually true. So let's go ahead and find, using our function, what the value is at 4 years. Which would be 22,295 times 0.895 to the power of 4. So let's go ahead and calculate that. 22,295 times 0.895 to the power of 4. And we get 14,305. Okay, obviously this was at exactly 4 years, so it is roughly close. You could see that they are very close in price. It's only like about $100 difference. So you can see, yes, it is in fact after 4 years. Like let's say maybe if I tried 4.01 or if I tried 4.1 or something like that, then it would probably be closer to that 14,210. So it is approximately 58% of the original cost. Okay, so last question, let's go ahead and do the challenge question for this topic. So we have radium's most stable isotope, radium-226, has a half-life of approximately 1,600 years. The half-life of a substance is the number of years it takes for half of the substance to decay. So that's what the half-life is, if you didn't know. Half-life is just how long it takes something to reach half of the substance. So in 2005, 40 grams of radium were stored. In 6 half-lives, there will be less than 1 gram of radium remaining. Select the appropriate definition for the variable x for the equation that models the amount of remaining radium. So what they're just saying is, what is x? So x is the number of half-lives that the radium has been stored, or is x the number of years it takes for there to be less than 1 gram of radium remaining? So in this problem, notice that they said that this question is looking at how many half-lives have passed. So the input x is the number of half-lives that have been stored. Notice it said in 6 half-lives there will be less. So this is the input and then this is the output. So the input is measured in half-lives. How many half-lives have passed? So for part A, it is the top one here. Part B says selects the most appropriate domain for the equation that models the amount of remaining radium. Now, we can't say that we have all real numbers, okay? We can't say that we have all real numbers for an input because we can't have a negative amount of half-lives. And also, if you're going to have, after 6 half-lives, there will be less than 1 gram of radium remaining, that means that you're really almost reaching 0, right? So you will be going, this is decay, right? So if we can imagine the graph, right? We start somewhere and then we're going down. And they're saying that at 6, it's less than 1 gram. So that's almost nothing. So the correct domain would be from 0 to 6. You wouldn't continue to infinity because now you're saying that that would be a negative amount of the radium, which is obviously doesn't make sense. So this negative amount gets cut off. So the domain for the real world problem would just be from 0 till 6. And then part C says, select the equation that can be used to model the amount of remaining radium. Okay, and the correct equation here, okay, they all have the input of 40, which is perfect. The exponent would be x, because that is, you know, the number of half-lives that have passed. And of course, because this is decay, you're losing, half-life is how much you're losing of the substance, right? How long it takes to get half of the substance to decay. So you would subtract, not add. So the correct equation here would be the first one. All right, guys. So hopefully that was helpful with those extra examples, and this makes a lot more sense.